Okay, I was originally going to do this myself, but there's been some confusion for those of you who've seen the list. So Charles from Cisco is going to sit in and jump in and out, and we'll bounce off each other as we go through the presentation. What I'm going to talk about today is some practical design implementation techniques for dynamic packet transport and spatial reuse protocol. So we're going to throw another coin into the hat, I guess, in terms of the technologies you've seen today. It's been a good fit for the three presentations today in terms of the technology. So what I want to cover today as we go through is just a design overview. What are we trying to achieve with this new technology? How will it benefit us? What are the advantages? Why should we be looking at using rings that are optimized for packet transport only? Some current design techniques that people are using for packet optimized rings. How we can remove the transport layer from our network and hopefully get to some type of IP over glass technology. DPT basics, what is DPT, how does it work? I think that's where Charles will probably come in and give me some input. Robustness and resilience, how can we use this technology in an environment where telcos demand the resilience and the robustness that we all see in the networks today. And then a very brief look at a planned case study which we'll be carrying out in the next 60 days at Verstel Telecom in the Netherlands. So I'll push on. Okay, so basically the brief is to effect the migration from a traditional transmission technology to a next generation platform optimized for the transmission of purely packetized data. That's what we're going to try and aim for through this talk to see how we can achieve that today. So why should we be looking at packet rings? Basically what we're trying to do here is lower the cost, capital expenditure to build ring architecture networks. So if we can remove SDH and SONET ADMs, adjunct multiplexers from our network, we can significantly reduce the cost to build this infrastructure. We want to find more advantageous use of bandwidth, more efficient use of bandwidth. So we can look at things like statistical multiplexing and spatial reuse to make sure we can use all rings as efficiently as possible. And we want to try and get our management infrastructure as simple as possible. So let's look at how we can find a single management infrastructure. Jump in whatever you want. Okay, the current design we're all familiar with is two rings, counter-rotating or counterclockwise, depending on how you want to look at it. Breaking off SDH tributaries, OC3 or above, onto I'll put packet over SONET. Breaking off onto our router. So that's the design we're all very used to. So we're going to look at this. We're going to try and look at this, see how we can remove those ADMs, but still keep the resilience and robustness of that design that we're all used to, so we can keep up SLAs, etc., etc. Okay, so while this design is robust, it can be inefficient when dealing with purely packetized data. As you all know, there are dedicated time slots for protection. So basically, we reserve one ring at all times for protection. We have to commission provision circuits. Regardless of the actual bandwidth use of that circuit, customer might want a PVC at whatever rate, but they may be sub that rate 90% of the time. So we can't really statistically multiplex our customers to achieve the highest and most efficient use of the bandwidth in our network. So we're going to look at ways to overcome that. And as we remove transport layers from the network, we can reduce cost and complexity, which is something we're all certainly after nowadays. So what we're used to seeing in terms of configuring a normal network over SONET, for example, is we'll have a router with a commissioned PVC across the working ring and one protection ring backed up. For backup. So we actually have to have the reserve bandwidth on the working. We have the reserve bandwidth number one on the working ring, and number two we have the protection which is enforced on us. So we have a double hit there because we've got a fixed circuit. The customer may not be using all the bandwidth that he's requested in that. So we're actually taking a hit on the customer's behalf. So what we're going to try and do is now remove that. So let's have a look where we are today. Traditionally, we can see. Is there a laser pointer up here? Is there a laser pointer?
Laser pointer.
You had one, there was one up here.
Anyone have a laser pointer?
Doesn't matter, it's okay. We're all used to seeing IP over ATM or IP over frame running on a SONET backbone it's a pin. With an optical carriage system, IP over ATM. Today we're at the packet over SONET type stage. Where we're trying to go to lower cost, complexity and overhead is towards the IP over glass solution. Get out the ADMs and just pop the IP straight onto the glass. Obviously there are framing issues, etc., etc., but we'll look at those as we head towards tomorrow. DPT, what is it? and let's look at the basics. DPT is also a ring architecture, except we remove ADMs and put in routers with DPT cards. Two loops, architected slightly differently. We have one outer ring which has two functions. One is to contain the outer ring data, and two is to contain the inner ring control. And then the inner ring does the opposite. It contains the outer ring control and the inner ring data. So we've got the outer ring, which runs around here, which has the outer ring data and the inner ring control. And then the inside ring has the outer ring control and the inner ring data. We also have built-in optical bypass for broken loop pass-through on the router. Ooh, two. I feel like, what's that guy from Star Wars? So as you can see, there's no ADM here. It's routers only. So we're getting closer and closer to just having IP on our network. Do you want to add anything to the slide? Two rings, inner and outer. Data and control are always in opposite directions. That gives us some failover capacity or ability, which I'll cover a little bit later. Both fibers are used concurrently, both for working and for protection. And there's accelerated control propagation for adaptive bandwidth utilization and self-healing, which is a bit of a mouthful. But basically means we can propagate any changes through the architecture very quickly and extremely adaptively for self-healing. It utilizes SONET SDH framing, and it runs over all key fiber transport technologies. It'll run over dark fiber, WDM, I'm not sure about DWDM. Yep, DWDM, yep. SONET SDH point-to-point and ring architectures. This is where I think we're all interested in bandwidth multiplication. How can we get an N by factor into our networks? This is achieved by using the spatial reuse protocol, or SRP, as some of you may have heard. Traditionally, a ring technology such as SONET, for example, will use source stripping. Basically, as the frame goes around, the source must strip it off the ring, which means it has to go around the whole ring to get back to the source. SRP actually allows destination stripping, which means that the destination will strip it. So I might pop back to a previous slide. So say, for example, if this is the source and this is the destination, in typical architecture that we're all used to, traditionally, the frame would need to travel around and be stripped and taken off here. In SRP, it's stripped by the destination, which means it only needs to go here. So we have an immediate bandwidth saving. We don't need to carry the frame around the rest of the ring. That's saving number one. Okay, so just to summarize, destination stripping allows the destination node to remove the packet from the ring, freeing up bandwidth and on other non-related paths. Again, look at the bandwidth multiplication. It's a dual fiber ring. Both fibers carry working traffic, which is slightly different to the SONET architecture that we're used to. SONET will allocate time slots, which is used for protection bandwidth. Implementing DPT in an existing network can yield you a 1 to 2 or a 2 by multiplication factor on your bandwidth. You can use statistical multiplexing because you're now at an IP layer. You can statistically multiplex your traffic rather than having fixed PVCs for customers who may not actually be utilizing that bandwidth on your infrastructure. You can statistically multiplex. There's no time division multiplexing and node provision circuits. You can actually oversubscribe, and you can't with SDH or SONET type technologies, and you can handle elastic burst requirements very easily because you're now playing in the IP realm. So what we're looking at here is just moving everything as close as we can to getting the IP on the fiber with nothing in between. Robustness and resilience. So coming from a telco environment, this is something that telcos are very interested in. Well, how resilient is this? How can we have our robust and resilient systems running on this technology? And in fact, is it? Is it robust? So we're using intelligent protection switching, proactive monitoring and self-healing through standard SONET and SDH overhead bytes. So it actually does include the standard SONET and SDH overhead bytes. So you can talk directly, say, for example, to one of your SDH boxes. 50 milliseconds self-healing layer 1 wrapping we were talking before. In the previous talk about self-healing. So this actually does provide for the SDH standard 50 milliseconds. Protection switching hierarchy for multiple concurrent failures. If you have multiple failures inside your rings, it'll actually provide protection switching for that as well. Just to continue on, it doesn't rely although it includes, it doesn't rely on SONET overhead bias. So you can actually run DPT over non-SONET technology such as WDM. It actually also provides, because you're now closer and closer to the IP layer, it provides for 50 millisecond IP restoration, which we're assuming won't affect IGP, but we haven't actually tried that yet on our network. And we've actually now, our network is now multi-layer aware. The router can now see all 3 layers. Well, we're trying to remove one of them, but it can see all layers clearly now. Do you want to add anything before I go on? Okay. Plan case study. We're looking to move a portion of our network into the DPT technology as a trial to run IP services and voice over. So what I'm going to do is go through what we've identified as the four identifying factors, and then we'll go and have a look at exactly what we're trying to achieve in the Netherlands. Single node SDH tributary has your SDH ring with an SDH tributary talking DPT with SONET framing back to your ADM, popping into your IP cloud. It's very similar to what we're all seeing now with the packet over SONET technology. Then we've identified a semi-hybrid, which is popping routers on either end of your SDH network, your SONET network. However, the IP is actually end-to-end. There's no commissioned PVC between the ADMs. So your IP is end-to-end. And then there's a hybrid network, which is popping a SDH tributary at OC3 or above at either end, popping it off another ADM at somewhere else in your network, running it across a cloud of whatever transmission technology you wanted to choose, whether it's IP, frame, SONET, ATM, whatever. And then back to a separate router. This is quite actually useful for dispersed networks. And then we can look at a full DPT network with routers in the core running DPT at OC12 speeds, breaking off OC3, running POS or even DPT again out to the edge. IP end-to-end again. There's no SONET, there's no ATM, there's no frame. So it's an IP-only end-to-end solution. The transport layer is completely transparent. You actually never see it in this example. Okay, just a quick look at what we're doing. We trench and run our own network around the Netherlands. So we've currently got some fibre running at the moment from Amsterdam to Den Haag to Rotterdam, Antwerp, down to Brussels, and then back up to Amsterdam in a loop. We're aiming to move this loop on a spare pair at the moment onto a DPT backbone for some voice trials. So we've identified a 3-phase implementation. We're going to go to the semi-hybrid trial, which is just running this on a point-to-point DPT link. Then we're going to go to a full hybrid trial, which is actually lighting all these with DPT on the loop, but breaking off on the switch on an OC3 tributary, not necessarily straight off the SONET. And then a full DPT loop running DPT on the entire lot, breaking off DPT everywhere. So unless you wanted to add anything, I think I've come to the end of the presentation. It's not up there at the moment, but if anybody wants this presentation, it'll be available at this address when I get off the stage, or you can email me. Yeah. Any questions?
Okay, great.
Let's hope I can answer them.
Quick question. My name is David Kaufman. I'm from Argonne Networks. A lot of your test phases seem to show running DPT on what's essentially just a point-to-point link.
Yep.
And I'm wondering what the advantage of that is over, just standard packet over SONET.
It's more of an education process for us at this point. If I go back one slide, you'll see that we're going to move very quickly down into the full DPT loop. That's where we're spending most of our time. So it's more of a familiarity phase for us to get used to it, look at the technology, see if we can find any scaling issues just in the point-to-point with traffic issues. For example, pushing large amounts of traffic over it. I know there have been some trials, I think in Germany, some other people here might be familiar with.
To answer your question directly, the point is actually the major difference if you were to build this on a POS as opposed to on a ring using SRP is that on a POS it will be one IP hop away. So you're actually doing IP packet processing in every hop you actually pass through. On an SRP ring, as you're not interested in receiving the packet, you just bypass through the node and it just gets forwarded onto the next node, and then whichever node is interested in receiving the packet, that's the packet that will actually receive the packet and then strip it off from the ring if it's a unicast packet and then send it out for processing the layer 3. That's a big difference between the two of them.
But in the strict point-to-point applications, which were several of the steps along there, is there really any effective difference? For instance, when Amsterdam and Brussels are a DPT link and the rest of it isn't, does it matter?
Ideally, if you have if let's say for example there's only one span that's already in the ring, then what happens is on the other, because remember you're dealing with a ring, so you have like a east-west kind of connection. So if only one span is a ring, then the other side of the ring will wrap, right? You need to have, to be able to do like a test, you need to have a ring to do a test, and you can actually break the fiber to form a ring.
Thank you.
Hi, my name is Evan Moore. I'm interested in hearing some more details on exactly how you work your intelligent protection and how you manage your spatial reuse. You just sort of breezed over those as they're here, we do them. How do you do them?
Okay. Why don't I go back to the slide? Do you want to cover it? Oops.
Your first point on spatial reuse is basically just a notion of actually taking advantage of destination stripping. So take for example the unicast packet, where the only party that's actually interested in receiving the packet is actually the destination node. So as the source node actually injects the packet onto the ring, the destination will strip it off from the ring. So now if you think about FTDI, for example, where the frame travels the entire span of the whole ring, spatial reuse is a notion where you actually strip at the destination point. Obviously for multicast type traffic, you actually have to traverse the entire span of the ring. So that's the only time when you get traffic that will traverse the entire span of the ring. And that brings traffic management kind of discussion as well. So how much can we oversubscribe? And I guess at this point in time is what's the ratio of unicast versus multicast traffic? And what wasn't mentioned here is actually there's no token that actually circulates around the ring. Okay, if you're familiar with FTDI, for example, you know there's a token that grants you access to the ring. All nodes on the ring has equal access to the ring. Okay, until the point when you hit congestion, that is when what is referred to as the SRPFA, the fairness algorithm will kick in, and at that point it will actually inform the congestion, the nodes upstream to basically throttle back. Okay, and this will move on until it hits all the nodes that's causing the congestion. So you can actually create what is referred to as the fairness domain within the ring. So take for example, can you go back to that slide where they have the map?
The map, yeah.
So yeah, take for example, like you have the direction of the ring, let's say, is for example this way here, and let's say you have Antwerp, Rotterdam, Den Haag, and then you reach Amsterdam. Amsterdam realizes there's a congestion here. Amsterdam will kick in the FA and will notify Den Haag, Rotterdam, and Antwerp to slow down. Okay, but then over here it's not affected. So now you created a fairness domain, which is this section of the ring here. Okay, so this is very useful when you have a big ring architecture. Now coming to your point on intelligent protection switching is basically very hierarchical. So if you know, for example, how SONET does protection switching, it's the same method. So there's hierarchies of protection. So you start at the very top level where you get signal fail. So if you don't see light in the fiber, for example, what you do. So you can have like signal degrade, for example, let's say between Amsterdam and Den Haag, you wrap around this signal degrade failure, and all of a sudden you have a fiber fail between Antwerp and Brussels, and here you wrap and you unwrap this section of the ring here. So as much as possible, try to preserve not to wrap the ring, but if all else fail, then it will cause a wrap. Router software do crash from occasion, and we have a special kind of like an optical bypass, if you will. So as long as you got power going to the box, when the router crash, it will automatically go into pass-through mode, and it will just bypass any packets that goes through it. So it doesn't actually wrap the ring unnecessarily. I hope that answers the question.
Thank you both.